Hello, everyone. So today we'll be presenting our dual security system with link signature keying and optical wireless communication using software-defined radio. We are a mixture of two research teams from UMass Boston, the UCAN lab headed by Professor Michael Ram, and the UMB Wave lab that is headed by Professor Casey Patel. We have 5 undergraduate researchers underneath these two labs. So there's me, John Carlo Laude, Rosalind Agasti, Arsalan Ahmed, Zachary Garns, and Miles Toole.
Our project is a dual security system used to send information from an access point to a user over a secure RF channel. There are two subsystems to this project, an RF channel and an optical wireless channel. Our novel dual security protocol is made up of two separate encryption methods. Link signature keying, which uses the impulse response of the RF channel seen by the transmitter and receiver to dynamically generate an encryption key. The other is an out-of-band dynamic optical wireless key distribution, which sends a key from the access point to the user in order to decrypt the transmitted information. Both protocols are not 100% secure. With LSK, an eavesdropper can experience the same impulse response up to a wavelength away, and with OWC, an eavesdropper can access direct line of sight through windows or keyholes. Combining the two creates a more secure system and is the motivation behind this project. This protocol does not require key storage or distribution, which is a key advantage to many existing encryption approaches. Also, the OWC out-of-band key can be dynamically changed without having to physically change the system like you would with LSK by itself. Here's a block diagram of our project. The RF subsystem is in blue while the optical subsystem is in green. The sensitive information is sent over the RF channel, which is encrypted with the OWC key. This key is sent to the user over the optical channel, which is encrypted with the LSK key. The user sees the same impulse response of the RF channel as the transmitter, so they can dynamically generate the same LSK key in order to decrypt the optical channel, giving them access to the OWC key to decrypt the information.
For the implementation of the RF subsystem, we used GNU Radio and the OFDM blocks built into them. The link was set up by sending a text file through the OFDM channel with certain noise, and the LSK keys was derived using the channel estimation data at the receiver. This key from the receiver side is saved to a text file. To implement the channel reciprocity of LSK, we set up a duplex model which derives the LSK key as observed from the transmitter side. This is also saved to a text file through a file sync. Now we had to determine the minimum number of bits for the LSK key, and we used the worst case SNR of the channel estimation from the transmitter and receiver end. After this, the flow graph is simulated to verify if the RF link is encrypted appropriately. Here is the output for the simulation results of this text file transmission in time domain. This is the initial text, and this is what we received. Similar simulation results were done for different noise voltages of the channel, and the following table shows the keys generated by each model. Notice that as the noise channel is increased, the minimum number of bits required to accurately represent the key also increases. In addition to that, since the transmitter experiences the same channel as that of the receiver, both the LSK keys match with each other. For the hardware testing of the RF subsystems, we used the NI2901 USRPs and vertical antennas that were set to operate at 1.75 GHz. A text file was sent through the OFDM transmitter and then demodulated at the receiver. Here's the demonstration. This is the hardware setup to test the data link in the RF channel. As you can see, there are two USRPs with the vertical antennas connected to each one of them. This implementation basically tests the LSK key generation process in a simplex model, that is, in a one-way transmission and reception setup. The frequency domain graphs verify the successful reception of the data file. And if we switch this over to the time domain display, then we see the same thing. This was the initial text file that was sent, and you get the received text file, which is pretty much the same, except for the errors which we did expect due to the different channel.
Let's now demonstrate the working of our out-of-tree OWC channel block. This is the flow graph where we have two transmitters and two receivers. On the transmitters, we have sinusoidal signals with different frequencies. After running the flow graph, we can see the two sine waves, which includes the 10 kHz signal at Tx1 and 1 kHz signal at Tx2. The current relative positions of the transmitters and receivers are shown on the top right. Since the corresponding TX-RX pairs are separated, we can see an almost perfect reception of the corresponding signals at the two receivers. Now, let's consider moving RX2 away from TX2 as shown in the bottom right. This can be easily done in simulation by changing the parameters while the flow graph is running. RX2 now receives signals from both the transmitters, which is reflected in the time as well as frequency domain representations. Lastly, if we rotate RX2 towards TX2 from this new position as shown in the bottom right, due to the highly directional nature of OWC communications, RX2 gets a stronger 1 kHz signal from TX2, which can be verified from these graphs. This is the flow graph for the end-to-end OWC link simulation, which utilizes our custom-made OWC channel block along with the inbuilt OFDM transmitter and receiver blocks for transmitting and receiving a text file. In order to integrate a real-valued channel block with the complex signals of OFDM, we had to perform some up and down conversions. Furthermore, in order to model the physical system closely, we have added the LED frequency response along with some noise in the system. Upon the execution of the flow graph, we can see our data coming from the text file which is being transmitted as an OFDM signal. Next, the signal passes through the channel where the up conversion to 400 kHz and the impact of the frequency response around DC is visible. At the receiver, the OFDM signal is retrieved with some added noise and the OFDM receiver perfectly decodes the signal. If we increase the TX-RX separation, the noise becomes significant and the received data becomes distorted. By reducing the separation, we get back to perfect reception. So this is the input file while this is the output file that we are receiving. It can be seen that the errors start appearing at the point where we increase the distance while they get rectified once we reduce that.
The following video is a demonstration of the implementation of an optical wireless channel with the physical hardware using USRPs, bias Ts, and optical wireless communication hardware with LEDs.
So here we open up the OFDM receiver. And then we open up the transmitter to transmit the signal. Then the signal gets transmitted through the USRP and through our optical wireless communication system. And then we received it in the USRP, and we received the signal here in the GNU radio side as well. Then we check to make sure that the signal that we sent was correct, which should be some private info, more private info, which is correct. Hello, so this is our fully integrated dual link security frame. And in our dual link security frame, we have our RF subsystem and our optical wireless communication system. In our RF subsystem, we made an RF hierarchical block that generates two LSK keys, one from the transmission side and one on the receiver side, using this process over here. And our optical wires communication link block, we have a simple process using the optical wires communication blocks that we had from before and passing it through an LED frequency response as well. In the input signal coming into our file is this. So this is our input signal, and this is our optical wires communication key that we're passing through. Now, if we run our system, you can see that there's actually some issues with it, with the keys being misaligned with each other and not being perfect. And this is caused by issues with both systems not being fully synchronized with each other. So you can see this is our encrypted key and this is our decrypted key. As you can see, there's some minor difference between both of them. And because of that, our input and output signal also has the same issue with some discrepancies in between them. And if we open up our decrypted file, so right after decrypting the optical wires communication key, you can see that the signal that comes out is not perfect and there are some discrepancies in there as well. And if we try to open the output signal, due to the bad encoding, we aren't able to read the file because of the bad encoding. But overall, we're able to transfer information in between the two systems. We do need to work on that synchronization to make sure that the signal comes out perfect. And that's pretty much it.
The project results demonstrate the following. First is that the two subsystems are individually tested and verified. The RF subsystem uses link signature keying, and as a result, the keys update themselves dynamically depending on the channel complexity. This made the management and distribution of keys much more simpler. For the optical wireless subsystem, we established a secure communication link through the optical medium using key encryption. We also combined both these subsystems to implement a dual security framework in GNU Radio. However, the results indicated that even though the signal was received, it was misaligned due to some unresolved synchronization issues between the two subsystems.
Now let's go over some of the challenges we faced in this project. The first was the integration and synchronization issue that we just discussed. The other problem was that some of the blocks we needed for encryption were not directly available from GNU Radio. For instance, there were no processing blocks for estimating the SNR of the OFDM signals, so we had to research and find an algorithm to set up our own SNR estimation block. Also, for the optical wireless subsystem, we had to create our own out-of-tree modules to simulate and implement the optical communication links. For the project management, we faced some challenges with installing Linux and setting up the GNU radio environment. Adding to that, some of us were not familiar with the software-defined radios, so we had to learn it from scratch. Our project advisors also helped us with getting familiarized with GNU radio and the SDR hardware. And of course, since the project was done during the COVID-19 pandemic, there was an added challenge of working in a remote setting, which did not allow us to meet in person. To tackle with the situation, we made sure to have weekly meetings and use platforms like Microsoft Teams to communicate efficiently.
For the future work on this project, we hoped to fix the synchronization issue between the RF and optical wireless subsystems by considering the delay in the encryption process between them. After this, the subsystem will physically be tested with USRPs to verify the communication link is secure in scenarios where sophisticated eavesdroppers are present. Thank you very much for listening.